Hey, and welcome to this lesson where we're going to be making use of multiple blueprint timeline tracks to make our crystal collection behavior a bit more interesting. Okay, so we're going to make a couple more things happen while the crystal moves towards the player pawn. While the crystal moves towards the player, we're also going to make the crystal scale down and also make its point-light component change intensity. Now in the previous lesson, we made our code easier to read by making use of these blueprint functions. And looking at our timeline, I'll admit I could have named this better, and it's always important to name correctly. Instead of this timeline being called Alpha Blend Timeline, which is not a great name, we could rename this to something better. To rename the timeline, we can select it, and we can press F2 to rename it. Let's rename this to Collection Timeline. And the track we added to the timeline, named Smooth Lerp Alpha, can have a much better name too. So to rename this, I'm going to enter the timeline by double clicking on it, and I'm just going to select the track, and to select it I can just left click next to the track on the left, or next to the graph editor on the left, and you should see it go orange, and then you can just hit F2 to rename it, and we can name this Collection Progress. Now let's take a look at making this crystal actor scale over the duration of our timeline. The first step here is to store our starting scale for the actor. And we already have a function here called store starting values. We can enter this, and we can actually extend this function a bit here. We can store the actor scale in here. To do this, we can simply right click and we can type in get actor scale. And the one we're looking for is the function named get actor scale 3D. With the return value here, we can right click on this to promote it to a member variable for our blueprint, and we can just call this start scale, and we can hook this up with the execution pins with the lerp start location. And just to be consistent, we can actually rename this variable here. We can select it, and on the details panel we can just take out lerp and we can just leave it as start location. Now we can come back to our event graph, and we're going to be looking just after our timeline now, but I'm going to make you do the rest here. Interpolate your actor scale from your start scale variable we just created and make the scale interpolate to 0. And make sure to make use of the collection progress value on the timeline. Then encapsulate your code into a function and name the function scale crystal. So pause the video here, and if you get stuck, make sure to check out your move to player function because it's going to be very similar. So once you complete this challenge, come back to the lesson and we can continue. So to do this, we want to set our actor scale. So we can right click and we can call the set actor scale function, and we're going to grab the set actor scale 3D. We're going to hook this up next to the move to player function. So remember, it's coming off the update of the timeline. The timeline is going to update and it's going to move the crystal to the player, and it's also going to set the scale of our crystal. Now, what do we want to set the scale to? Well, we want to interpolate it. So we're going to drag out this input vector and we're going to type in lerp. And we're going to grab the lerp vector function here. Now we want to interpolate from our start scale variable we just created. So we can grab that off the variable tab and we can plug this into the A input. So it's going to interpolate from the start scale, and we want it to, we basically want it to shrink entirely. So we don't even have to put in any values into this B input because this is zeroed out completely. It's going to make our scale go from whatever the actor scale is to 0. But to animate it smoothly scaling down, we need to make use of this collection progress return value on the timeline. Okay, and that's all we need to do for this little task here. We can actually select all the nodes, and then we can right click on one of them and we can encapsulate it by collapsing it down to a function. And we can name this scale crystal. Now let's take a look at what happens when we come back to our level and hit play. We can see that when we roll towards these crystals, they are moving towards the player, but they're also scaling down over time. Okay, great. So let's just come back to our crystal blueprint because we're not quite finished yet. Now the alpha of our scale crystal is coming from the same collection progress return value on the timeline, but there's no limit to how many tracks we can add to a timeline. So we can add another float track if we want to, and we can call this scale progress. And we can hold down left shift and left click to add keys, just like we did above. We can set the time and the value from them. We can add another one. We can set that to the length of the timeline, which is 0.68 seconds, and we can set the value to 1 as well. So we've got the exact same float track as above. Now remember, the first keyframe means that we are at the starting scale of the actor, and the final keyframe, if it's at the value of 1, this means that it's going to be all the way on the B input of our lerp here, okay? So it's going to be, the value of 1 is going to be equal to the actor having 0 scale, so it's going to be completely shrunk down, invisible. But just like there's no limit on how many timeline tracks we can add, there's no limit on how many keyframes we can add here. We can create some pretty interesting behaviors in relation to scaling our crystal just by adding another keyframe. Now what happens if this keyframe outputs a negative value? Well, this would mean it would actually increase the actor's scale. Looking at this lerp diagram here, we can see that if you move from A closer to B, we would be scaling the actor down, but moving from A away from B, we would be returning larger values, and as a result, we would start scaling the actor up. So I really encourage you to experiment with these keyframes and do share your results in this lecture's discussions on the Resources tab. You can see my results here. When I collect my crystal, it inflates a little and then deflates at the same time as moving towards the player. Okay, so right now I have a final challenge for you. Create a new timeline track named Light Intensity and store your starting light intensity. Then interpolate your light intensity to 0. And of course, make sure to encapsulate your code and name the function adjustLight. So have a go at this final challenge, and I really encourage you to experiment with the timeline, and then once you're ready, come back and we can wrap up this lesson. So I've created my timeline track, I've named its light intensity, and I've added some keyframes, and you can see I've got a bit of a zigzaggy pattern going on here. Now, back in the event graph, I want to start by storing my light intensity. So I'm going to come inside the store starting values function, and we can grab the crystal light component, we can drag it out, and we can get its intensity. And we can promote this to a variable. And we can just name this start light intensity. And we want to make sure we hook it up to the execution pins and make it straight on the execution flow there. So that's looking good. We can come back to the event graph, and now we can take a look at interpolating our light intensity. We'll start by grabbing the light component, and we want to call the set intensity function. We can hook it up to the execution pin here, and with the intensity, we want to interpolate the value. So we can drag it out, and we can type in lerp and get the lerp float function. And this works the exact same way. We can grab the light intensity from the collection timeline, and we can plug that into the alpha. The A input here is going to be our start light intensity, and the B input is going to remain at 0. Okay, so we're going from the starting light intensity, whatever that is, and that is about 20,000 units here. So we got the scale of going from 20,000 units to 0 on the lerp. Now we would want to take a look at encapsulating this code here. So we can just select all the nodes, select one of the nodes, and collapse it down to a function, and we can name this adjustLight. Okay, so I think this is looking good. Let's come back to our level and let's hit play and let's see what happens. So we can see that the light starts blinking, it starts scaling up and down, and it's also moving towards the player pawn. Okay, so this is looking really good. Now looking at our code, the only final thing I'm not happy with here is just this get player pawn and this equal operator and this branch here. But this branch has 2 output execution pins, and we can't make a blueprint function return multiple execution pins. So in the next lesson, we're going to be taking a look add a solution for this. Hello and welcome to this lesson, which is all about blueprint macros. We're going to use blueprint macros as a replacement for a function because it allows us to work with additional execution pins. So looking at the blueprint code for our crystal blueprint, we can start to see that it's becoming a lot clearer to read because we've encapsulated a lot of our code down into functions. Now, the only thing we're not really happy with is where we do this equal check from the overlap. Okay, so something overlaps with the crystal and we check to see if it's the player pawn, and if it's the player pawn, we then continue on executing our blueprint code. But there's a problem here. The branch has two output pins. It's returning two output execution pins, but functions can't have multiple output execution pins. So if we can't collapse these down to a function, we need a solution. Is there something that we can do to collapse these down into a node that's similar to a function? Well, yes, there is. We can use blueprint macros. So we know that blueprint functions can have input parameters, and blueprint functions can return values as well. But blueprint functions cannot have multiple input or output execution pins. So we're going to have an issue here if we want to collapse this code down into a function, because it returns two output execution pins. And this is where blueprint macros come in handy, because blueprint macros can have as many input or output execution pins as we want, and we can even name the execution pins. So to create a blueprint macro, we can look towards the My Blueprint tab, and we can come down to the macros section, and we can add a new macro here. Let's name this macro isPlayer. Now looking on the details panel, we can see we can add inputs or outputs, and currently our macro has no input execution pins or output execution pins. So to add a input execution pin, we can hit new parameter, and look, it's already given us the execution pin type here, and we can give it a name. We could just name this execute. And we need to add another input parameter because we need to check an actor and compare it to see if it's equal to the player pawn. So we can drop down the type here and we can search for actor. And we want to grab the actor object reference, and let's give the input parameter a name. Let's just name this actor. And now I'm going to challenge you to finish this macro off. Create two output execution pins on your macro. Name the first output isPlayer, and then name the second output notPlayer. And for the final step, add your compare code to this macro. So the code where we compare the other actor to see if it's equal to the player pawn, and where we use the branch, we want to add this code to this macro. Okay, so pause here, and once you finish this, come back to the lesson and hit resume. Okay, so to finish this macro off, I'm going to add a new output pin. I'm going to make sure it's an execution output pin, and I'm going to name this isPlayer. I'm going to add an additional output pin, and this is going to be notPlayer. So we have two outputs on this macro now, one for if it's the player and the other for if it's not the player. Now we need to add the code into this. We've already got the code in our event graph here, so we can just select all of this. We can hit Control X to cut it, and we can come into the macro and paste it in. And we can just move and organize our nodes here just to make it a bit neater. So we've got this input actor pin. This can go straight into the equal check here, and we want to make sure we hook up the entry node to the branch, and then the true output for the branch, if it's the player, it's going to go to the isPlayer output, and if it's not the player, it's going to go to the output named notPlayer. Okay, and that's all our code in our macro here, and then we can drag the macro onto the event graph, and we can hook up the execution pins, and just make sure we input the other actor from the begin overlap event into this, and then the isPlayer output is going to go to the store starting variables. So something causes an overlap with our crystal. Is it the player? And then if it is, continue on with our collection code. And we can see that it's a lot easier and neater to read now. And if we come back to our level and hit play, we can see it still works just as expected. Okay, so that wraps up this lesson on blueprint macros. We can see how encapsulating our code into macros can be helpful if we require additional execution pins. And if you had any additional questions or wanted to showcase your work up to this point, I encourage you to use this lecture's discussions on the resources tab for this lecture. Okay, so in the next lesson, we're going to step away from our crystals to create some projectiles that will cause damage to the player. So when you're ready, I'll see you there.